Hello again. We are going to continue with some more examples for limiting and excess reagents. In your text, page 296 to 303. And again, same objectives as our last lesson. We're going to be performing calculations to determine the amount of reactant consumed or product yielded in a chemical reaction. And we're going to try to identify limiting and excess reagents in a chemical reaction. A reminder of our definitions. The limiting reagent in a reaction is the one that's completely consumed. It's the one that drives a reaction. Once it's all gone, our reaction stops because one of our reactants is gone. The excess reagent is not completely consumed, which means there's going to be a little bit left over. It's present in more than the required amount. Again, we're just going to display some of our formulas again. And all of these formulas are now fair game for our calculations. Here they've all been solved for moles, but we can isolate any variable in any one of these equations in order to get the quantity or the value that we need. And so we'll go with an example. So here we have a volume of ammonia gas being produced when some hydrogen gas and nitrogen gas are mixed. So assume standard conditions throughout the reaction. We want to find the volume of ammonia gas when we have a certain amount of hydrogen and a certain amount of nitrogen gas. So the first thing we need, this is a formation reaction, so we need to write a reaction down. So hydrogen gas, H2, and nitrogen gas is N2, and it's going to make ammonia. So NH3, and again it's a gas. Now we're going to balance our chemical reaction, and I'll start with the nitrogens. I need 2 nitrogens so from my reactants, so I'll put a 2 in front of my products. That gives me 6 hydrogens, so I'll put a 3 in front of my hydrogens. So there's my balanced chemical reaction, and I'm just going to list the things that I know. And so I have 39 moles of hydrogen gas, so my volume is 39.0 milliliters. My volume of nitrogen gas is 15.5 milliliters. We want to find the volume of ammonia gas produced. And it's all at SATP. So, normally what we do is we find the number of moles of each reactant. And then we'd use our mole ratio to find out which one produces less. However, because we're working with gases, I talk faster than I can write to find out which produces less. Now, because we're working with gases, and because it's all under the same set of conditions, so we're using gases, and we're using the same conditions, so same conditions for reactants and products, we can use our law of combined volumes, which basically means for gases, the volume ratio is the same as the mole ratio. And it only works for gases, and it's nice because it lets us skip a step. So we can go directly to the volume of ammonia by using our law of combined volumes. And so we can say the volume of NH3 produced is going to be, if we check with our hydrogen, it's going to be 39 milliliters times a mole ratio of 2 over 3. And so we're going to get, if we multiply by 2 and divide by 3, we'll get 26. If we check for nitrogen, we'd say, well, there's 15.5 liters, or milliliters, and now our mole ratio is 2 over 1, so we're actually going to double it. So double that would be 31. So there's our two volumes. This is if H2 is a limiting reagent, and this one is if N2 is a limiting reagent. And we look at the one that produces less. So the one that produces less is our hydrogen. So once we use up all of our hydrogen, we'll have 26 milliliters of ammonia gas. If we were to use up all of our nitrogen, we'd have 31 milliliters of N2 gas. Since this one produces less, H2 is our limiting reagent. So 26.0 milliliters of NH3 is produced. And so the nice thing with gases is if we keep the same conditions from beginning to end, we can use our volume ratios instead of converting to moles and then converting back into volumes. Let's try another one. Here we have manganese metal and aluminum oxide are produced by a reaction between manganese 4 oxide and aluminum. So determine the mass of magnesium produced when 1 kilogram of each reactant is used. So as soon as we see that we know both, or an amount for both reactants, we know we're going to have to do a limiting reagent problem. Because we know how much of each reactant we have to see which one gets used up first. And so we'll look for our reactants here. We have manganese 4 oxide. So manganese is Mn. And 4 oxide means we're going to need 2 oxygens. And it's a solid. To it, we're going to add aluminum. It's aluminum metal, so just Al, solid. Our products are, so it's going to be single replacement, it's going to be aluminum oxide and manganese metal. So we'll write down the manganese first. In the end, it really doesn't matter which one gets listed first. So manganese metal and aluminum oxide, and so it's going to be Al2O3 for aluminum oxide. And now we're going to balance our reaction, and we'll start with, I guess, the oxygen, since we have more oxygens than anything else. We need 2 oxygens, or we have 2 oxygens on one side, and 3 on the other. There's no way to balance them with just one number unless we use a fraction, so instead what I'm going to do is I'm going to say, well, if I put a 2 in front of my aluminum oxide, and a 3 in front of my manganese oxide, that'll balance my oxygens. So I'll end up with 6 oxygens on my reactant side, 6 on the product side, and now I can balance my metals. I'm going to need 3 manganese and 4 aluminums. So just by going after that most common element first, it makes balancing a lot easier. And so the other thing we know is the mass of manganese and the mass of aluminum. And we want to find out the mass of manganese solid. So we have 1 kilogram of each thing, so we're going to have to convert to moles, which means we're going to need molar masses. We're going to need a molar mass of manganese 4 oxide and the molar mass of aluminum. Aluminum metal, just straight off the periodic table, is going to be 26.98 grams per mole. And the molar mass for manganese oxide is 86.94. And so now we're going to find out how much each of these will produce in terms of moles of manganese. The one that produces the least is our limiting reagent. So, for manganese oxide, we would say the number of moles of manganese oxide. And now I gotta write down my formulas before I forget. Because all of these are molar mass formulas, the only formula we really need is mass is equal to mass over molar mass, and then it's just different manipulations of that formula. So the number of moles of manganese oxide is equal to mass over molar mass. So 1 kilogram would be 1,000 grams divided by 86.99 grams per mole, and we'll end up with 11.5 moles. Now that we have the number of moles, we're going to find out the number of moles of manganese oxide. We're going to find out the number of moles of manganese is equal to 11.5 moles times our mole ratio of 3/3, which would be the same as 1/1. So we end up with 11.5 moles if manganese 4 oxide is our limiting reagent. So now we're going to check for aluminum and see if aluminum is our limiting reagent. And so we're going to find out how many moles of aluminum we have. Again, mass over molar mass. And now we're going to have 1,000 grams divided by 26.98 grams per mole. And we get 37.1 moles. And it's not enough to stop here. By looking at the number of moles of reactant we have, that doesn't tell us exactly or directly how many moles of product are being produced. So we got to get an extra step, and we're going to find the number of moles of manganese. So it's a 37.1, and now our mole ratio is 3/4. I should put my moles there. So multiply by 3, divide by 4, and we end up with 27.8 moles. And then we take a look. The one that produced less was our manganese oxide. So manganese oxide is our limiting reagent. The aluminum would be the excess reagent. And now we can continue with this number and figure out how many grams of manganese are produced. So the mass of manganese produced is the molar mass times the number of moles. The molar mass of manganese, and we forgot to write it down the first time, so I'll write it down now, is 54.94. And so it's going to be 54.94 grams per mole. And we're going to be multiplying that by the 11.5. And now when we go back, we're going to use a little bit longer number. If we use the 11.5, there's a chance that we're going to get a wrong answer because of rounding. So we're actually going to go back into your calculator, and I'm just going to write down a few more extra digits. We won't need all of them, but even if we do an extra 2, we need 3 sig digs total. So by having 5, we shouldn't make any errors just because of rounding. So we'll use 11.502. Multiply that by our 54.94, and that is 632 grams of manganese solid. There we go. So, in terms of stoichiometry, it's pretty much the same as our first stoichiometry problems. Just have one extra step. We've got to find out which one of our reactants is a limiting reagent, which one's excess, and use the limiting to continue our calculations. Here we have one more example. A 1 gram sample of aluminum hydroxide is placed in 50 ml of hydrochloric acid with a pH of 3.62. We want to determine the mass of water produced by this reaction. So, first we need a reaction. We need aluminum hydroxide. So it'll be Al, OH3 because aluminum is a 3 plus metal. It's a solid because they gave us the mass. Plus hydrochloric acid, so HCl. And because they said acid, we know it's aqueous. And they react to produce. And it's going to be a double replacement reaction, in this case a neutralization because it's an acid and a base. We're going to get AlCl3. And if we check our periodic table, or not our periodic table, but our solubility table, every time we make a compound, we've got to check that solubility table and make sure that what we produced is either aqueous or solid. When I take a look, we find our chloride ion. Most positive ions, or most cation ions, are aqueous when they're with chloride, and aluminum isn't in the exceptions. So we have aluminum chloride aqueous and H2O, and H2O is a liquid when we put it in water. And now we're going to balance it. And what I see here, I see 3 hydroxides for my aluminum, so I know that I'm going to need at least 3 waters to balance those hydroxide out. Remember, we can think of water as being HOH when we're balancing our equation, and this OH here is our hydroxide. So 3 hydroxides, that's going to give us 3 hydrogens, so we need 3 hydrogens for our hydrochloric acid, which is nice, because we needed 3 chlorides as well. So there's our balanced chemical reaction, and we're going to write down things we know. We have a mass of aluminum hydroxide, and we have the pH of an acid, which is really a sneaky way of giving the concentration. So we've got to find the concentration first, because we can find that it's going to be the inverse log of negative pH. And they also gave us the volume, so the volume is going to be 50 milliliters. We want to find out the mass of H2O produced. So because we need the mass of H2O, we're going to have to use the molar mass, 18.02 grams per mole. We're also going to need the molar mass of aluminum hydroxide. So the molar mass is 78.01. Whoops. 78.01 grams per mole. And now we can get started. We can find out the number of moles of each of our reactants and get the number of moles of water produced and see which one makes more. So we'll start with aluminum hydroxide. We're going to use number of moles of Al, OH3 is equal to mass over molar mass. And see here, I get so excited about doing these problems I forget to write down the formulas I'm going to be using. So I'm going to be using my molar mass formula. I have to use my pH for my concentration, so concentration of H3O, and because it's a strong acid, this is going to be the same as the concentration of HCl. Because it's a strong acid, these two things are going to be equal, and it's going to be the inverse log of negative pH. Just when you thought you could forget about that chapter 6 stuff, it comes right back. So we're going to be using that formula. We're also going to have to be using our concentration is equal to N over V formula. And that should be about it. So we're not going to be using our gas law formula, but otherwise we're good to go. I should have picked one that produced hydrogen gas, then we could have used them all. Alright, anyways, just a chemistry teacher's dream, I suppose. 1.00 grams over 78.01 grams per mole. And we get 0.0 0.0128 moles. 0.128 moles. And now we can find the number of moles of water produced. 0.0128 moles times 3 to 1. And so we get, I'll write it down here, 0.0385 moles. So that's how many moles of water we'll get if aluminum hydroxide is our limiting reagent. And now we're going to check for HCl as our limiting reagent. And so to find the number of moles, the first thing we've got to do is find the concentration. So concentration is equal to the inverse log of negative 3.62 so we get a concentration of 2.399 times 10 to the negative 4, which means we're going to have to find number of moles. So the number of moles of HCl is going to be concentration times volume. Sorry, we're going to write down our units here. This is moles per liter. Our concentration is 2.399 times 10 to the negative 4 moles per liter times our volume, which would be, oops, where did my pen hop to? 0.05 liters. Make sure we do that, convert those milliliters into liters, otherwise we can't cancel our units properly. And so we get 1.199 times 10 to the negative 5 moles. And now we can probably tell what our limiting reagent is. This hydrochloric acid, there's hardly any of it there compared to the number of moles of aluminum hydroxide, so it's probably going to be our limiting reagent, but we're going to do our last step just to make sure. So the number of moles of water produced by our acid would be 1.199 times 10 to the negative 5 moles, and our mole ratio is 3 to 3, or 1 to 1, so the number of moles isn't going to change, and this is definitely much smaller. 1.19 times 10 to the negative 5 moles. If you can't see the difference between these two numbers, we can always rewrite this one in scientific notation. We've got to move our decimal spots 2 spots to the right here, so it would be 3.85 times 10 to the negative 2 moles. And when you have scientific notation, compare the exponent first. Times 10 to the negative 2 is bigger than negative 5. Negative 5 is a smaller number, it's more negative, so we have less water produced by our hydrochloric acid. So our hydrochloric acid is our limiting reagent. And now we can find out the mass of H2O produced. So we're going to be using this number of moles here because it's smaller. So mass of H2O is going to be molar mass times moles, 18.02 grams per mole, times 1.199 times 10 to the negative 5 moles. We're going to get 2.16 times 10 to the negative 4 grams. And when we take a look at our question, don't forget that for pH, there's only 2 sig digs for our pH, so it's going to be 2.2 times 10 to the negative 4 grams. That's the mass of water produced by our reaction. So there's some examples for limiting reagent. There's some more practice problems on page 303. Good luck, and I'll see you